We know that the Moon orbits around the Earth, although more precisely the Earth and the Moon orbit their common center of mass. But because of the big mass difference, that center of mass is inside the Earth, near its center. The orbits of all planets are ellipses, but in the case of the Moon around the Earth, it is very close to a circular trajectory. As a matter of fact, we can also make a first-order approximation of the orbit of the Earth around the Sun as a circle. If the Moon moves in circles around the Earth, it's because it experiences a centripetal force which is constantly changing its trajectory. This centripetal force is the gravitational force. This force is radial, which means that points from the Moon to the center of its trajectory. Because there is this centripetal force, the Moon experiences a centripetal acceleration, which is written as mass of the Moon times its speed squared over the radius of its circular trajectory. But, as I said before, this centripetal force is the force of gravity between the Earth and the Moon. G mass of the Earth, mass of the Moon, over the distance squared. Here the distance is that between the center of the Moon and the center of the Earth. The distance, because we assume that the Earth does not move and only the Moon does, is the same as the radius of the trajectory. From here we can solve for the velocity of the Moon in its stable circular orbit. V is equal to the square root of g times the mass of the Earth over the radius of the trajectory. Look that this result does not depend on the mass of the Moon, only on the mass of the Earth and the distance Earth to Moon. This calculation is valid for any satellite, natural or artificial. So if we want to put an artificial satellite in orbit at a distance r from the center of the Earth, this is the velocity that it needs to have in order to be in a stable circular orbit. It looks familiar to the escape velocity, but that one is a square root of 2 times larger. If you launch a projectile from a certain height with a velocity smaller than this one, it will eventually fall back down. If you launch it with this velocity, you will put it in orbit, assuming no air resistance. This is a key concept. You don't realize that the same force and phenomenon that makes an apple fall to the ground is the same that is keeping the Moon in stable orbit around the Earth. Because the force of gravity on the satellite is radial and the position vector is also radial, the cross vector of position times force is 0. This means that the torque of the force of gravity on the satellite is 0 and therefore the angular momentum is conserved. From this we can conclude that for elliptical trajectories, when the satellite is closer to the Earth, its speed is greater, and when the satellite is farther from the Earth, its speed is smaller. May science be with you.